I'm Larry Forsley. I'm with JWK International, and we're a collaborator with SPAWAR. I've been following their progress for 20 years and became very actively involved in the last 4. A lot of the work that I've been doing with them has been in the nuclear diagnostics, looking at both charged particles and neutrons and gamma ray emanations. This particular slide shows a scan using a tassel scanner for CR39. And what you see here is 1 millimeter swath of a piece of CR39 that is 1 centimeter wide and almost 2 centimeters long. So it's compressed in the Y direction. And on the front side, you see a series of tracks that are in fact coincident with 3 separate cathodes we had on there. We had a gold, a silver, and a platinum wire. On the back side, we also have tracks. Again, roughly coincident with the gold and with the platinum, but virtually nothing associated with the silver. And we discovered these by accident. Again, Gary Phillips, as Frank had mentioned before, he and I were scanning these with a tassel scanner on the East Coast, and it turns out that day Pam was scanning some of these on the West Coast in San Diego, and within probably a few hours of each other, we had realized that we had been looking at the front and the back and unexpectedly found tracks on the back side. And the significance of this is that for a proton to go from the front to the back would require over 10 MeV. For an alpha particle to traverse this, it would take over 40 MeV. So the question became, if these are not charged particles, what's causing these tracks? Well, we have a second piece of information. If we look at the distribution, the number of counts versus the major axis of somewhat maybe elliptical tracks, we find that on the front we've got basically 3 populations. One which is around under perhaps a micron, one around a few microns, and the bulk of them are in a range of about 5 to about 15 microns peaking in here. From our calibrations, this area here more or less corresponds to perhaps a few MeV alpha particles. However, if you look at the distribution on the back, it's significantly different. You have 3 populations. You have a few of these small ones. You have a larger population here. But what's noticeable is this large hump that actually continues out past 40 microns. Now, if indeed this was caused by a charged particle going from front to back, generally, the faster the particle, the more energy it has, the smaller the track it leaves. So a 40 MeV alpha is not going to leave a large track. It's going to leave a small track. On the other hand, these are consistent with having neutrons come in. And on my next slide, I'll show what this actually looks like. On the left-hand side, this is from plutonium oxide, which is a natural fission source placed on top of a piece of CR39 and looking on the back side of it. So the neutrons are released, they pass through it, they interact with the carbon, hydrogen, or oxygen, they knock those particles through, and then when we etch them, as Pam said, you'll bring some of these tracks out. What's very noticeable, though, is all these smaller tracks. These are latent tracks. Because the efficiency of CR39 is so low for neutrons, on the order of 1 in 100,000, you can sequentially etch through, and you keep bringing up new tracks. These latent ones will become full-blown. You keep etching your way through. In our case, using a silver and palladium on the back side, you find the same kinds of tracks, and you find the same latent tracks in there as well. Now, there are basically 3 mechanisms by which these tracks can appear from the neutrons. Because the neutrons being neutral, they'll just pass right through. They've got to encounter one of the atoms, and you can have an event here where you get a recoil where you'll hit, say, a hydrogen, you'll knock the hydrogen through, and the neutron will stall within. You can actually get a spallation. You can knock a proton out and pick that off, or actually have the carbon or oxygen come through. Or if you've got sufficient energy, what will happen is you'll hit, for example, carbon or oxygen, you'll actually shatter it, and you'll end up with 3 alphas coming off. If you look at a plot of the major axis versus the count, this is a log scale, it turns out you can do neutron spectroscopy this way. And again, this is from the work of Gary Phillips, who with DOE and Ditcher funding went through and characterized these detectors to see if you could essentially identify different energy neutrons. And what you'll find is as the energy of the neutron goes up, you get larger tracks. And you have a region here which are due to recoil protons, a region around 25 microns, which correspond to recoil carbon and oxygen, and then there's a region around 35 microns, which is the 3 alpha breakup. And as I note down here, can't read it from this angle. Oh, here we go. Gary's calibrated this from 114 kilovolts all the way up to almost 15 MeV. Now, if we superimpose the data that we've taken in our analysis, you find the following. Again, log of counts, the major axis across the bottom axis. So we take a 2.5 MeV neutron source, in this case a DD fusion tube, and a 14.8 MeV neutron source, which was spallation from a cyclotron. These are in red and in blue, and you'll find out that you've got a distribution. In the case of the 14.8 MeV, you actually have recoil carbon oxygen, but you have this peak down here, you've begun to shatter the carbon. If you look at ours from the palladium deuterium co-deposition, we overlay on top of that, and in addition, we also have these peaks out here. Now again, as I said before, one of the ways to confirm that these are in fact neutron recoils as opposed to some artifact is to sequentially etch. We normally etch for about 6 hours. In this case, Pam has etched for 60 hours, and we're actually going now for 53 microns of plastic removed, and these two latent tracks are beginning to come out, and this track that was closer to the surface is now getting much, much larger. And again, using the dual focusing, you can see these have the typical shape, and because these may be coming in normal, the neutrons may be coming in normal, but when you're going to have these scatter off, you'll have them going in almost any direction, and that's exactly what you see right here. These are consistent, in fact, with the neutrons you'd find from DD and DT fusion reactions, where in the case of DD, one of the channels gives you a triton and a proton, but you have another channel where you get a 2.5 MeV neutron coming off, plus a helium-3 with under 1 MeV. You have a DT reaction, which gives you a 14 MeV neutron, bracketed between roughly 12.5 and 15.5 in the data that we've taken. We have a colleague, Andrei Lipsin, who took CR39 to a cyclotron in Russia and mapped out the energy versus the track diameter and plotted these out. This is now just looking at protons. He then went through and sequentially etched this and found that although he couldn't easily differentiate these at say 6 to 8 hour etching, if you etch longer, you can in fact differentiate these, and that means you can differentiate protons in energy between say 1 and 2.5 MeV. Taking that data, he then produced a plot that shows the number of counts versus the recoil energy, the protons, and in this case we're now looking at the recoils from the neutrons that came in and impacted CR39. And this particular data was actually taken at a co-deposition experiment done at SRI. First, he's overlaid on here a californium source, and that has a peak around 2.5 MeV, which is what's known for californium. It's a spontaneous neutron generator by spontaneous fission, and it has a tail that goes out actually as much as 5 or 6 MeV. What we see with the data from the CR39 from co-deposition is a nearly monochromatic source of neutrons, because it cuts off very, very sharply above 3 MeV. Well, we've now characterized the potential that we've got DD fusion neutrons. Now we look at triple tracks. This is from the literature, and what happens is a neutron comes in. If it has over 9.5 MeV, it has enough to make up for the binding mass deficit between carbon-12 and 3 alphas. Any additional energy then goes into driving these alphas, and you can see that you get a variety of different positions. What's happening is the neutron comes in, and there's a tendency for it to go in the forward direction. But in fact, it will go off almost isotropically. You may have one of the alphas coming back towards you as you're etching. In addition, the CR39 plane that you're etching is here. You don't know where in the CR39 the neutron's going to impact it. So the distances and the angles that you get can be very arbitrary. If you look at our data, you'll find a whole cluster of potentially charged particles and neutrons. You'll find a triple track here, and these are from 4 separate experiments run, focusing on the top surface and then focusing at both the top and down at the tip where you're getting scattering. And you can see a variety of different shapes here. A little bit closer up, you can see again, you've got the 3 alphas coming off, and this is again very, very similar to what you find in the literature. Now we can go one step further. We can now measure the distances in each of these, And if we come up with the rest mass difference, 9.6 MeV, and then we measure each of these distances and run them against the LET curve, in other words, how far an alpha of a given energy will go through CR39, we can then plot out each of these and come up with the energies of each of the alphas, and we come up with 12.33 MeV. Now, this is also an underestimate because, again, I don't know what angle theta is associated with each of these axes going back into the CR39. But consistently, the work that we've done has shown these to be between 12.5 and about 15.5 MeV. Now, taking the information that we've got and the observations we've taken you saw before, these ejector cones are almost always 50 microns across in our case. If I calculate the volume, say I have a radius of 25 microns, and again, I'll underestimate and only say the depth is 25 microns. Given the melting point and the vaporization point of palladium, what I come up with is it takes on the order of 5.8 times 10 to the minus 2 joules to vaporize this quantity of palladium. If I assume I've got DD and DT fusion reactions occurring with the normal branching ratio of 50% into each of the two DD channels, then I would need on the order of 30 billion fusion events to vaporize this amount of material. Now, what's very significant about this is if you look at the CR39 we've got and what I showed before, you'll see that there are recoil tracks on the backside associated with the cathodes. If you add up all of the neutrons that we see times the inefficiency of CR39, we have on the order of 100 million to a billion neutrons that we see across the entire CR39. Yet what this is saying is that we've got on the order of 30 billion fusion events with 30 billion neutrons being produced. And the answer is that not all of this heat is being produced by conventional DD and DT fusion reactions. I would make the case that this is a strong example that there are at least two channels in this system. And looking at some of the possible nuclear pathways, I come from the hot fusion community in laser fusion. We start off with tritium, so you have a DT reaction to begin with, and you get the 14.1 MeV neutron. In fact, these triple tracks are referred to as nuisance tracks in the laser fusion community because you want to use the neutrons to diagnose what's happening in the core. So when you get triple tracks, they tend to obscure what other broadening of the track energy you've got. And we do the same thing. We're making use of the neutrons as a diagnostic to know what's going on inside the system. Running through the rest of these reactions, you come down to one mentioned before by Rob, that you get D plus D going to helium-4, about 10 to the minus 6 times, producing a gamma ray that's hard to see. And then we have another reaction, which is perhaps the thermal channel of cold fusion. This one produces only heat and has no gammas. So it may be that we have evidence of this happening in the system we've seen. In addition, there's a variety of tertiary nuclear reactions possible. If you've got energetic charged particles and neutrons, you're very likely going to get ash of some kind when these impact other things, both the charged particles and the neutrons, and in fact we've seen that in terms of the elemental transmutation. Now, one of our colleagues, Mitchell Swartz, has gone and plotted out this data and come up with what he calls the optimum operating points, that there are points in terms of, in his case, electrical power versus the heat coming out, and for different ranges, for tritium, for heat, and for heat in the gas systems, you find that there are optimum power points to operate at. And this is one additional interpretation of the data, but if in fact this is correct, this would begin to give us a sense, there we go, would give us a sense of how to control the system. But what I'd noticed in some of our data and some of George Miley's data is there may in fact be a tendency to overshoot the optimum point, perhaps for heat or for charged particles. And at this point, I'll turn it back over to Frank.